Hello, this is the Heartbleed exploit. I'm Algus.
I'm Tom.
I'm Hassan.
All right, let's begin.
So to start off, we're going to go over some important terms. Transmission Control Protocol, or TCP, which is a protocol that establishes a reliable order and zero-check connection between two important applications. And the second one is Transport Layer Security, TLS, a protocol that ensures secure communication over a network by encrypting and authenticating client-server connections. And lastly, OpenSSL, which is open source library that implements SSL, which is a frame center to TLS and TLS protocols, providing tools for encryption, certificate management, and security communication.
So, a summary of the Heartbleed vulnerability. It was discovered in 2014, and it affected versions of OpenSSL from 1.01 to 1.0.1F. The exploit type is a buffer overread, which allows attackers to read more sensitive data than intended. What made this bug dangerous was its simplicity. An attacker only needed to send a single malformed TLS request to get sensitive data and read more than it was allowed to. The security impact of this, it could expose up to 64 kilobytes per request without any authentication, and it didn't leave a trace of its attack either. This could leak things like session cookies, private keys, as well as user credentials. Its reach, it affected 66% of HTTPS service at the time, and this affected sites like Yahoo and GitHub. This took months to fully patch the bug. The bug.
All right, so I'm going to go over I'm going to do a quick overview of the actual vulnerability that allowed this exploit to happen. So this exploit targets the heartbeat protocol. This is a thing that the servers do to verify connections. The TLS clients sends a heartbeat request, which the server echoes back. The bug here is that the vulnerable OpenSSL version has a function TLS1 process heartbeat with no bounds check for the payload length. This means that if the payload length is greater than the actual received bytes, it'll allow for a memory overread leak of data located after the buffer on the heap using memcopy. The impact of this is that the leaked data will include private keys, cookies, login info, and other TLS session memory. So to further explain the heartbeat protocol, you can see down here in the table, the expected behavior is that the client will send a message like ping with a length attached to it to the server, and the server will echo that back. But as you can see in the exploited behavior, they send the message ping. The length is way larger than the length of ping, and then you get all that extra sensitive data. Another picture is this. I found this cool comic from XKCD, which also illustrates this. I'm gonna collapse down my Zoom thing so you can see everything. I thought it was funny, so. All right, so let's talk about how we recreated this exploit.
So for the base, so we first start off with basic setup. So we had a emulated x86 Linux environment across all platforms. And for instance, OS used VM, and Windows it used VirtualBox. And we selected a common Linux distribution, which 1.2.4. And we installed essential packages, essential to begin for GB Python and requests. And for the web server setup, we downloaded OpenSSL version 1.0.1F, and we also downloaded Nginx, which is version 1.6.0. It's the latest stable version with minimal dependencies. This is a web server. And we also statically linked OpenSSL to Nginx, which serves Nginx users, uses our compiled OpenSSL and avoids issues with shared library mismatches during runtime or debugging. And this works with the web. Okay. So we ran the LD dash engines, which listed dynamic dependencies, and OpenSSL was not shown as this means it's directly linked. And we also ran object on dash the engines, grab heartbeat, and just make sure that the vulnerable function is present, and the heartbeat function was found the vulnerable version of OpenSSL is being used. And this is all the command we have used to build the entire server and all that. Let's see here.
So running the actual web server. To run the server, we ran this command, and we had the flag daemon off on it because we included the flag daemon off so that the server runs in the foreground, helping us debug easier in GDB. The server was set up to run on localhost at port number 11443, and we ran this to verify that the server is actually up and running. We did the flag dash k, so we would not have so it would ignore certification validation, and this outputted a static HTML page which confirmed that the server was running over HTTPS.
So now onto the exploit itself. So this process was really simple and only took really 2 steps. So the first step was injecting a session. We did this inside a Python file we called alice.py, and we ran this command. This Python file pretty much, yes, included only this one line. So we connect to this, we send a GET request to this URL, and we pass in this cookie, which includes a session cookie. We call it ultra secret cookie because it's secret and no one's supposed to know it. And then the goal is to use the Heartbleed exploit to leak this ultra secret cookie. It simulates a real user hitting the HTTPS endpoint with a secret session cookie. The next step of the exploit is to send the malformed TLS heartbeat request. So this is done inside a different Python file we called hb or heartbeat.py. This involves sending a malformed TLS heartbeat request with a fake payload length OXFFF, which is around 64 kilobytes. It's the maximum length we can send. And this allows, this causes this, this file prints, on run, prints the server response to the console. And then to verify this, we just saw that, okay, the cookie's leaked in the dump and the exploit is successful. So let me just show you a few pictures of this. So alice.py is here. We have this ultra secret cookie here and the GET request. Heartbeat is more complex. If you notice here, there's a thing that says client hello. Most of the functionality is you can just read what it says on the comments, but this big block of text isn't commented. That's just like key generation information and the date time of the actual request being specified here. And then yeah, so we just like attack it by sending in we send the client hello to establish a connection, and then after that we send the bad heartbeat request to do the actual exploit. And this is the output. So we run Alice first again, and then we run the heartbeat. And then you can see in this big dump of bytes that we have the ultra secret cookie hidden right there. So success. So let's do a bit of an analysis on what we found and like other information about this exploit.
So for setting and triggering the victim, so first and we run the following command, and then we this is kind of effectively how we have broke down the process of how we get into the triggers exploit. And if we look at the disassembly of the TLS1 process hardly.
So looking at the disassembly of the programmable function, the TLS1 process heartbeat, you can see that the function takes a length, a source, and a destination from the stack and passes them into the call to memcopy. The issue is that there is no validation of the length value before copying memory. That means if the attacker sends a length much larger than the actual data, the function will copy way more than the memory than it should, leading to an overread. This diagram on the right shows what the attacker's input looks like just before the memcopy call. The attacker sets a very large length of FFFFF, which gets pushed onto the stack along with the source and destination addresses. Since there is no validation, the function copies far more data than intended.
All right. So quick summary. So the attacker will pass this very large length. The TLS process heartbeat does not check for this. And then the memcopy reads past the expected heap memory, leaking private keys, credentials, session data, and other sensitive information. A possible fix that we found for this is just doing a very simple check. Check if the payload length plus 3 is greater than the packet length, then return 0, right? Fail. And if the official fix does pretty much exactly this, it validates the payload length against the message size before memcopy and rejects the oversized heartbeat requests. So basically, it's been patched.
So for the final takeaway from the session, obviously what we have learned is that a very simple bug like this bounce check issue can prevent catastrophic leaks. And binary exploitation can succeed even without crashing it. And that real world vulnerability simple but overlooked. And from our technical standpoint of view, is we debug TLS memory handling with CDBM breakpoints. We verify the mem copy overread via register inspection, and we trigger live memory leaks using a Python-based proof of concept. And for teamwork workflow, we divided the setup, debugging, and documentation tasks, and use Discord and shared emails to stay ahead.
Thank you so much for listening.